Now we are going to look at why actor model. How how do we choose uh, instead of object-oriented programming, multi-threading programming versus an actor model? So if we take the OOP multi-threading, the threads have shared memory. So objects accessed by multiple threads, the same resource is accessed by multiple threads. So when we do this, there can be multiple issues that can happen. uh, but in the actor model, message passing between independent actors, each with its own isolated state. So there is no shared memory, all isolated within the actors. Uh, Data shared, so in the traditional one, shared state. So to maintain the accuracy, it needs to be locked. The locking condition needs to be done, and synchronization needs to happen. If one thread is modifying it, it need to be synchronized to others. So and the race conditions can happen if one is reading an object value, and it is and another one is reading the same value, and if this updates the value, and for this thread it has the incorrect on an old value which is not the correct one. So these are race conditions. So all these issues can occur, and this handling of this locking mechanism can be pretty complex also. Here none of those how do you say, locking mechanism, race conditions, synchronizing between the threads is nothing matters, because it is not applicable. Here this entire model, actor model, resolves and removes this complexity of the multi-threading scenarios. uh, so no shared access, so it's all isolated, its own state, and no locking needed. Mutex, semaphores, these are not needed. And exception handling also, let's say when something goes wrong in a thread, it can impact normally those are handled with try catch blocks, typically in the method level. But in the actor level approach, these are handled in with inside the actors with the supervision strategy, using restart or resume, which is more clean approach. Scalability, this resources can't be accessed by infinite number of threads, so there's some limitation. But here this limitation is very high, highly scalable. Fault tolerance is also, when something gets failed, there is resource get locked or something like that, the other threads can get impacted also. Here it's not the case, everything is isolated, so if one failure doesn't impact the others. And uh, communication needs synchronization. If one is working with an object, others needs to be synchronized, but here there is nothing. All the messages are passed as immutable ones, so to the each actor, so it's not modified in between. So it's really clean. And as I said before, deadlocks can occur, race condition, synchronization can occur. This concurrence control is needed here. Here it's not needed at all. It's all kind of built into the actor itself, reducing the complexity. And this is more good for application for minimum shared data, light tight control over concurrency, a small, very tight monitoring is needed. This is okay. But here, if you need highly concurrency, highly scalable, highly distributed stateful application where message based instructions are more natural, this will fit more. So with multi-threading, it heavily relies on this shared memory and locks and synchronization. So this is very complex and more prone for concurrence issues. Actor model is a successor for, I mean, not a next successor, but a good approach compared to that for concurrency, and emphasizes in isolated state and asynchronous communication, and it is more fault tolerant and more scalable in comparison. So this is the comparison between both of